Trigonometry involves triangles. It involves the relationship between the angles in a triangle and the sides of the triangle. In the cases we are going to be dealing with, it will only be right-angled triangles, and we're going to look at the ratio of two sides. That really compares how much bigger one side is than another, compares their sizes. To refer to the sides, we need to label them. Hypotenuse is opposite the right angle, just as in Pythagoras' theorem. The side we label opposite means directly opposite the angle we're dealing with. So A looks out on O. The remaining side is next to the angle. Adjacent means next to. So the side that's next to the angle is labelled A. So that's the side between the right angle and the angle A that we're dealing with. So that's how we'll label the sides. Consider this triangle. If I extend the two sides, draw a line parallel to this red side, I've got two equiangular triangles, the smaller one here and the bigger one. These two angles are equal because they're in an F shape, that's corresponding angles, and we have parallel lines. Same reason, these two angles here, which are right angles, are the same. So equiangular triangles are similar. One is a scaled up version of the other. If I put in parallel lines, I generate several equiangular triangles. The biggest one here is 3 times this smaller one, because that's 12 boxes here, and it started out as 4 boxes. So this big triangle is 3 times the smaller triangle. This one here is 8 boxes for the red line, double that 4 boxes. So the scale factor here was 2. So this triangle is twice as big as the smallest one. This triangle here has the red line 6 boxes from the original 4 boxes. It's 1.5 times bigger. Scale factor was 1.5. For this one, where it's 10 boxes, the scale factor was 2.5. So each triangle is a scaled up version of the other. If we look at the ratio within the triangles, the ratio of the opposite side to the adjacent, that is this red line. So that's the red side to the green side of the triangle. Here, red is 4, and that's 6 for the green side. Ratio 4 to 6, 4/6. The next one, that's in the red line 6 boxes, and along this green side is 9 boxes. 8 in the red boxes, 12 in the green boxes. 10 for the red line. This green side is 15. In the final case, the red line is 12 boxes, and right along the bottom here, the green side is 18 boxes. These fractions came from 4 multiplied by 3, it gave you 12, because the big triangle was 3 times bigger. And the 6 also had to be multiplied by 3, because the green side was 3 times bigger. So it gave us an equivalent fraction, 12/18. And so on for the rest. They're just scaled up versions of 4/6. You multiply the top by a scale factor and the bottom by a scale factor, which cancels itself out. You end up with the same fraction. Not just 4/6, but they're all 2/3. You all simplify to 2/3. So basically this angle, opposite to adjacent, is always 2/3. As long as you don't change that angle, it won't change from being 2/3. So with this angle is associated the ratio 2/3. That angle is approximately 33.7. 33.7 has associated with it 2/3. It's the ratio in a right angle triangle of the opposite side to the adjacent side. No other angle has the ratio 2/3 in that right angle triangle. For the ratio 2/3, there's no other angle associated with it but 33.7. They're uniquely paired. So 33.7 and 2/3 go together. No other angle has that pairing. To illustrate this a little further, here is a setup with 33.7 degrees, 4 boxes, 6 boxes, that's opposite over adjacent, 4/6, 2/3. As long as I keep that angle at 33.7, there it is, 33.7, 6 over 9, 2/3. There it is again, 33.7, it's 8 over 12, 2/3. It doesn't matter how big I make the triangle, as long as that's still 33.7, the ratio is still 2/3. The only way to change that 2/3 is to change that angle. So if, for example, I were to slightly change this angle to 3/5, it's now 31 degrees. 31 degrees has opposite over adjacent 3/5. As long as I keep that at 31 degrees, the ratio should stay at 3/5. So there it is, it's 31 degrees, 6 over 10, 3/5. As long as that's 31 degrees, this won't change from being 3/5. As long as I keep the ratio at 3/5, it'll keep the angle at 31 degrees. So every angle in a right angled triangle has an associated ratio opposite over adjacent. It's a unique ratio for a particular angle. Now, excuse me, this ratio opposite over adjacent is called the tangent ratio, abbreviated to tan. So that's 2/3 is the tangent ratio. On the calculator, there's a tangent function. If you put in tangent 33.7, it should give you 2/3. Now, it won't quite give you 2/3 because 33.7 is a rounded answer here. If you have 2/3, above the tangent buttons, the inverse tangent button, tan with a wee -1 on it, that takes you from the ratio 2/3 back to the 33.7. So tangent takes you from the angle to the ratio. Inverse tangent takes you from the ratio back to the angle. Here it is here. If I press tan 33.7 in the calculator, up comes this number, not quite 2/3. If I put in shift tan in the calculator, that's inverse tan. So inverse tan 2/3, up will come, well, not quite 33.7, 33.69006 and a whole lot of figures. So the thing about trigonometry is, apart from a few exceptional cases, you don't get exact answers. So here it is in summary. Tangent ratio is opposite over adjacent in a right angled triangle. This is inverse tan. If you inverse tan the ratio, it will tell you the angle, so you can find an unknown angle. If you're told the angle, you can get the tangent of the angle, and if you get tangent of the angle, it tells you the ratio, which will enable you to work out an unknown side. And there are going to be 3 kinds of question where they might ask you to work out an angle, they might ask you to work out a side, but the side could be in the top of the ratio, the opposite side, or it could be in the bottom of the ratio, the adjacent side. 3 kinds of example. Here we go. Find the angle. We'll label the sides. H opposite the right angle. Directly opposite the angle we're dealing with, A degrees here, is 2. That's the opposite. The remaining side next to the angle is the adjacent. So we're dealing with O and A. That's the tangent ratio. There it is. So we would label the sides, and the first bit of important working is this. The tangent of the angle A is opposite 2 over adjacent 3. To find the angle, we need rid of this tangent bit. We get inverse tangent. So to find the angle, you need the inverse function. Inverse tangent, that ratio. You put that into the calculator, up comes a big long answer you write down, and you round it off. So that's 4 lines of working to find the angle inverse tan, the ratio. Next case, finding a side. Label the sides as before. We're dealing with tangents opposite over adjacent. Angle's 33.7. Tangent of the angle, 33.7, is opposite A over adjacent 3. So there is the first line of important working. Tangent 33.7 is A over 3. So we want to get A. To get rid of that 3 in the bottom line, we would multiply the left hand side and the right hand side by 3. 3 would get rid of the 3 in the bottom here. So multiplying the right hand side by 3 gets rid of the 3 in the bottom, and we multiply by 3 in the left to balance it. There it is. You can think of it as the 3 comes up to multiply the tangent function. Put it into the calculator, big long answer, and round it off. 4 lines of working, the letters on the top take the number up to join the function. It multiplies the left hand side here. 3 times tan 33.7. So that's the letter on the top of the fraction. Here's the same case with a wee twist to it, which is when we get tan 33.7 and it's opposite over adjacent, it's 2 over a. The letter's on the bottom. More awkward. In physics, you often turn formula around using this setup. So this is tan 33.7, 2 in the top, a in the bottom. 2 in the top, a in the bottom. Tan 33.7 is 2 over a. To get a, it's 2 in the top, tan 33.7 in the bottom. There it is. So notice, really, the a and the tan 33.7 swapped positions. So if the letter's in the bottom, you get that swap, and that solves it for a. And that goes into the calculator, up comes a big long answer you write down, and it rounds to 3.0. So that's 3 kinds of example. The 3 cases are: find the angle, inverse tan the ratio. Find a side with the letters on the top, take that number up to multiply the other side. And here with the letters on the bottom, swap them over. So, 3 kinds of example. There's a worksheet which you can download using the link in the description. It will have the answers. Here, only use the tangent ratio to find the missing angle. So download the worksheet or pause the video. Here's the second half of that worksheet. It's find the sides. Sometimes the letter will be in the top, sometimes on the bottom of the fraction. Only using tangent here. Find the value of the letters. So pause the video or download the worksheet. And here are the answers. Pause the video or get the answers from the worksheet. Here are the answers to the second half. Now if you download the worksheet, here it is. It will have the answers with it. You can also download the notes, which will show you examples for all the videos on trigonometry involving right angled triangles. The next video we'll be looking at all 3 trig functions, sine, cosine and tangent, and how to use them. Hope you found this video useful. Thank you.